Right. Okay, guys, welcome to topic 7.10, reaction quotient and Le Chatelier's principle. By the end of this, you should be able to explain the relationships between Q, K, and the direction in which a reversible reaction will proceed to reach equilibrium. Okay, so in 7.3, we saw that the reaction quotient Q is used for systems that are not at equilibrium, while the equilibrium expression K is used for systems that are at equilibrium. When a system is stressed, it causes a reaction to be out of equilibrium, and the reaction will respond in order to return to equilibrium. If we compare the value for Q to K, it can be used to predict the direction that the reaction will go to reach equilibrium. If Q is equal to K, we are at equilibrium. If it is less than K, the ratio of products to reactants needs to increase. Therefore, the reaction proceeds in the forward direction. The numerator's too small, so it's going to get bigger. Numerator's products to turn Q into K. If Q is greater than K, the ratio of products to reactants needs to decrease. We need to increase our denominator and decrease our numerator. Therefore, the reaction will proceed in the reverse direction to turn Q into K. Changes to the concentrations or partial pressures change the value of Q, but not the value of K. Changing the temperature will change both values for Q and K. The value for K will only change with the change in temperature. Consider the system A plus 3B yields C plus 2D, where K, the equilibrium constant, is 3.5 times 10 to the negative 4. The initial concentrations are 1 for all reactants and products, so 1 molar. As always, in an equilibrium problem, start by writing the expression, then plug in the initial concentrations to determine the direction that the reaction will shift in order to reach equilibrium. In this, we see that Q is greater than K. So since Q is greater than K, the reaction will proceed to the reactants to turn Q into the value of K. Now we can solve to find the equilibrium concentrations. Using an ICE table, we are going to organize the data. So we put in all of our initial concentrations. We are going to use the value X for the change and incorporate the coefficients. Remember to include the sign as it proceeds to equilibrium. So since we're going towards the reactants, that means we are going to make or add reactants and use up products. And then we bring down our coefficients. Oops, B is 3, not 2. And then in the parentheses is going to be X, because I don't know what that is. So then 1 plus X, 1 plus 3X, 1 minus X, and 1 minus 2X. You can plug, we're going to now plug, or you would plug these in to the expression up here. And given the fact that you have a bunch of numbers in this with exponents, you're going to have to use a solver for this. Okay. So, or you can graph it. So you're going to look for the zeros for this, and we're not going to do that in this one. We're going to do it in the next one. So we're going to consider this reaction between iodine gas and chlorine gas to yield iodide chloride. So reaction at 25 degrees C initially contains the following pressures. Find the equilibrium partial pressure of I2, Cl2, and ICl at this temperature. So remember our steps. The first thing you need to do is to write the equilibrium constant expression. So because it's pressures and we're given pressures, we got to write it in terms of pressure. So products, which is ICl squared over reactants, okay, so now that we know that and we know what Kp is, we're now going to write our Q, or not write, but calculate Q. So we have 0.1 squared divided by And when we solve this, we see that Q is 1. So Q is less than K, so we're going to shift in the forward direction. Okay, now we're going to take this and set up our ice table. So rewriting our reaction. And now setting up our ice table. Okay, we know all of our initial concentrations are 0.1. We know we're shifting towards the product, so we will make products and use reactants. And since it's the change, we use the coefficients. Okay, and those coefficients become, the change value is x, because we don't know how it's changing. Writing our equilibrium. Okay, so when we go from here, we're going to plug the equilibrium expressions into our equilibrium constant expression. So product is 0.100 plus 2x squared all over 0.100 minus x times 0.100 minus x. From above, our equilibrium constant value is 81.9, and that is equal to 0.100 plus 2x. And then these two, since they're multiplying, I can actually simplify that and because they're the same in the parentheses, and say that's squared. Well, this is squared over squared, so this is technically a perfect square right here. This whole thing is squared. And since that whole thing is squared, I can take the square root on both sides. So this cancels. And when you solve for x, going through a couple extra steps, you should get and find that x is equal to 0.0729. You use algebra to solve. So like those cancel, and you're left with the square root of 81.9. I can't remember what it was. Multiply both sides by the bottom, and then simplify your x's. So then using this, and we're going to plug it into the equilibrium expressions up here, the first one we can do is the pressure of iodine gas at equilibrium, and we do 0.1 minus 0.0729, which is 0.027 atm. And then the pressure of chlorine gas, same thing, because it starts off the same. And then the pressure of the iodine chloride gas is 0.1 plus 2 times this value, which is 0.246 atmosphere. Okay. And on the AP test, you'll be given something that is either a perfect square, something that you can do an approximation value, or something that works out easy. You won't have to use the quadratic formula to solve things on the AP test. It's part of the exclusion statement above. Okay, but for some of these, like this one, we may need to use a solver for the ones in class, because finding all the perfect ones is really hard to do. So why not work on hard ones, so when we get the easy ones, they're easy. Given the reaction A yields 2B plus C, where Kc is equal to 128, the initial values are provided in the table. Calculate the value for Q to determine the direction the reaction will go. Well, before you can do that, you have to figure out what K, the equilibrium expression, is. So it's always products of reactants, so the concentration of C times the concentration of B to its coefficient, because it actually has one, divided by the coefficient, divided by the concentration of A. So now we can calculate Q by using the same expression and the initial values provided. So 1.85 molar for C times 3.20 molar for B, and we're going to square that, divided by 2.50 molar. Simplifying by doing some math, we see that Q is equal to 7.58. Since Q is less than K, we need more products, so this is going to be a forward shift. Okay, what that means is that we're going to add here. Oops, not there. There's too many boxes. We're going to add here on the product side, and we're going to take away on the reactant side. We're going to bring down the coefficients, and then we are going to fill in X. So we end up with 2.50 minus X, 3.20 plus 2X, and 1.85 plus X. So now we can substitute these into our equilibrium constant expression and solve for X. So Kc is equal to 128, which now substituting in our expression, 1.85 plus X times 3.20 plus 2X squared divided by 2.50 minus X. Okay, so this is not going to be an easy one to solve for. What I would recommend is using a solver either on your calculator, if you know how to plug it in and solve for the zeros, or what I would do, or I did, is I used an online solver. This is the one that I just preferred. I think Desmos has one too, but you're going to use a solver for this and you should get X is equal to 1.50. Okay, note that this is harder than, or more complex than what would appear on an AP test, but this is more applicable to lab settings as well. So when we substitute in for X and above, so 2.5 minus 1.5 is 1.00. 3.2 plus 3 is 6.20. And then 1.85 plus 1.50 is 3.35. Okay, and so those are our equilibrium concentrations for this reaction. Okay, so practicing this, you have one where you're going to need to use a solver. I'm going to scroll to it. Oops. Number 3, you will want to use a solver for it, okay? Specifically C. So make sure you're using a solver and it'll help you do what you need to do. Okay guys, thank you for tuning in. Complete the you do and check your work.